Οπότε ας ξεκινήσουμε σιγά σιγά. Σας καλωσορίζουμε όλους στο πρώτο σεμινάριο για την φετινή ακαδημαϊκή χρονιά του τμήματος μας. Έχουμε μαζί μας σήμερα τον Νικόλαο Ιγνατιάδη, ο οποίος έχει κάνει, από ό,τι βλέπω, σπουδές bachelor τόσο στη μοριακή βιοτεχνολογία όσο και στα μαθηματικά στο Πανεπιστήμιο του Heidelberg, και τα έκανε σχεδόν ταυτόχρονα, εντυπωσιακό θα μπορούσα να πω. Έχει ένα master λοιπόν στο Scientific Computing από επίσης το ίδιο πανεπιστήμιο και συνέχισε με διδακτορικές σπουδές στην στατιστική στο Πανεπιστήμιο Stanford. Αυτή την περίοδο δουλεύει σαν μεταδιδακτορικός ερευνητής στο University of Columbia και αν δεν κάνω λάθος, περιμένει να διοριστεί στο Πανεπιστήμιο του Σικάγο μετά από ένα χρόνο. Νίκο, με διορθώνεις αν κάτι δεν είναι σωστό.
Σωστό.
Οπότε σε καλωσορίζουμε στο σεμινάριο του Τμήματος Στατιστικής και σήμερα ο Νίκος θα μας μιλήσει για Confidence Intervals for Non-Parametric Empirical Base Analysis. Νίκο, μπορείς να ξεκινήσεις να μιλάς. Όποιος θέλει μπορεί να ρωτάει ερωτήσεις καθ' όλη τη διάρκεια της παρουσίασης. Οπότε, the floor is yours που λέμε.
Ευχαριστώ πάρα πολύ για την πρόσκληση. Είναι μεγάλη μου τιμή που παρουσιάζω σήμερα εδώ και ελπίζω σύντομα να σας γνωρίσω όλους και από κοντά. Και χαίρομαι ιδιαίτερα που μιλάω για αυτή τη δουλειά σήμερα, καθώς, όπως θα εξηγήσω σε λίγο, το τμήμα σας είναι πραγματικά το ιδανικό κοινό για αυτή την ομιλία. Οπότε θα ξεκινήσω τώρα την ομιλία και θα παρουσιάσω στα αγγλικά. So today I'd like to talk about confidence intervals for non-parametric empirical base analysis. And to do that, I first need to tell you what empirical base is. An empirical base really means different things in different contexts or by different authors. So here I've listed some different topics in statistics that relate to empirical base. For example, very related to this department would be mixed models with non-parametric components. But all of these clearly relate to empirical base, but to be more precise about what I mean with empirical base in the context of this talk, I'd like to give a very concrete data analysis example. So specifically, I also like to talk about a topic that should be familiar to this audience, which is experience rating. So I'll go back to Switzerland in the 1960s, when several insurance companies wanted to increase the premia. And the Swiss government did not really want to allow it unless the insurance companies would assign the premium as a function of the past behavior of different policyholders. So to make things concrete, I'm showing a data set a specific actuary called Bichsel had access to. And this was the data set for one car insurance company in 1961. And for every policyholder, Bichsel knew how many claims that person had done in 1961. And the table on the left just shows a summary of this data set. So for example, 255 policyholders made 3 claims. And as I said, the goal would be to assign the premium for the next year as a function of how many claims each individual did in 1961. And Bichsel's idea was to essentially assign this premium by assessing the expected number of claims in the next year. In other words, to compute the expected number of claims in 1962 among people that had a given number of claims, let's say 3, in 1961. Of course, estimating this quantity without having data from 1962 requires making some additional model assumptions. So here's the model Bichsel considered. He essentially posited that the claims in 1961 for a given individual and 1962, they're both independent and Poisson distributed with mean mu I. And the crucial part is that this mu is indexed actually by the policyholder. And it essentially reflects, for example, how risky their driving is and other similar factors. And now I think the ingenious idea that Bichsel had was to try to connect all policyholders together in a joint probabilistic model by positing that the mu I themselves are random and they're all drawn from an unknown distribution G. And Bichsel called this the structural function representing the heterogeneity of the portfolio. You may call this the latent variable distribution, or you might call it the prior in a simple Bayesian analysis. And remember, what Bixel was trying to assess was the expected number of claims in the next year, given the number of claims this year. And it's easy to show under the probabilistic model I'm showing here that this is equal to the conditional expectation of the latent mu, given the claims in 1961. And throughout this talk, I'll actually denote quantities as they are above by theta with an argument z, which is what we're conditioning on. So here, for example, let's say 3 claims in 1961. And then the crucial part is I'm also showing this subscript g. So that's this prior. And what this notation is trying to emphasize is that if Bixel actually knew g, then this quantity could be directly computed. So let's say for a Bayesian, this quantity would be given. But Bixel actually did not know g, so he could not compute this quantity. But on the other hand, he had the data I showed you before. So basically then, this is where empirical Bayes comes into play, where Bixel tried to estimate g based on the data. And Bixel actually followed a parametric approach, but now I'd like to instead present a more non-parametric approach that would be perhaps a more modern approach that somebody might pursue nowadays. And the idea is the following. What we observe is the number of claims in 1961, which I'll just denote by Zi in for each individual. And we're also assuming that mu I come from this prior G. And we'll also make the structural assumption here that G lies in the set of all distributions that are supported on the set from 0 to 5. And I'll denote this by calligraphic G. And then in non-parametric maximum likelihood, you can try to maximize the marginal likelihood over all possible distributions. And if you do that for this problem here, you'll get this discrete prior I'm showing on the bottom left. And you can see that essentially policyholders cluster into 2 groups, some that make more claims and some that make less claims. And now one could pretend, or in the empirical Bayes approach, one pretends that this estimated prior is the actually true prior. And one can use it to compute, for example, the posterior mean, which would give the best prediction for the number of claims in the next year. So for example, for somebody that made 3 claims, the best prediction for the number of claims in the next year would be about 0.69. So the question I want to address in this talk is the following. In the last slide, I said that the estimated or the posterior mean or the expected number of claims in the next year is 0.69 for somebody that made 3 claims in 1961. But actually the way we got this quantity was by estimating the prior by non-parametric maximum likelihood based on our data set. And of course, this must induce some uncertainty. So this number 0.69 has some uncertainty. And if we want to use this number to, let's say, base decisions on, then we should account for this uncertainty. Now, the problem I'm actually described has a very elegant solution by colleagues in this department. So this paper by Carlis, Drougas, and Fragos. And essentially this paper, applying the method of this paper that I'll describe in a second, you can actually get a confidence interval for this quantity here. So here, instead of the point estimate 0.69, you'd get the confidence interval from 0.55 up to 0.80. So actually, even though the sample of this insurance company is quite large, there's still some uncertainty to account for. So let me quickly describe the method that led to these confidence intervals. Essentially, we'll do a model-based bootstrap approach. So G hat is not the non-parametric maximum likelihood estimator of G. And then for each bootstrap sample, we'll basically resample n new claims in 1961 under the hierarchical model we estimated. And then having n new observations, we'll just fit another non-parametric maximum likelihood estimator. I'll denote it by G hat B. And now the posterior mean, so our best prediction for the number of claims in the next year is again a new number that depends on the estimated MPMLE. So essentially we collect this number of bootstrapped estimates of the quantity we're interested in, and then the interval I showed was just the percentile bootstrap confidence interval based on these bootstrap samples. And now what the authors prove is the following. Under the model I described, and assuming that the unknown G lies in this class calligraphic G, where G is supported on a compact interval, and also another technical condition that essentially says that G has a density close to 0, then the authors prove that the confidence interval I showed has the right asymptotic frequentist coverage. So the true quantity we're interested in, the empirical base quantity, lies in this interval with probability at least 1 minus alpha asymptotically. And let me emphasize what this statement is claiming. So essentially the uncertainty here is taken with respect to the n samples, Z1 up to Zn. And the reason we even have to do this task is because we don't know G. And we basically have to estimate G and the estimate of interest based on the n observations. Is this goal clear? And the formal statement?
Yes, everything is good.
Oh, thank you. So this now brings us to the topic of this talk. So this is the paper with my PhD advisor, Stefan Bagger. And what we're trying to do in this paper is to essentially form confidence intervals for estimates as the one in the previous slide, but under a more general class of problems, still within the empirical base framework. So let me tell you how we generalize the model I just showed you in the previous slide, and how we think of empirical base in the context of this talk. So essentially, we assume that we have noisy data, Zi, on n units, and each unit has a latent parameter mu I. And then we make three assumptions. First, we assume that the distribution of Z given mu is known and will denote the conditional density by P. And one example in the application we talked about would be that Z given mu is just Poisson with mean mu. Then the second assumption, or the second ingredient we'll have here, is that the mu's themselves are random and drawn from a distribution G that's unknown, but we'll assume that G lies in a known class calligraphic G, and I'll give more details about this later. And the last ingredient is the empirical base estimate, that in this talk will take the following form. It's a conditional expectation or posterior expectation of a function h of mu given Z. And as before, we'll denote this by theta, with the argument Z, which is what we're conditioning on, and subscript G, which is the unknown prior. And H can be an arbitrary function specified by the analyst. For example, if H is the identity, then theta is just the posterior mean that we had before. And there's a lot of results in the empirical base literature under this setting. And there are a lot of results specifically for constructing point estimates of these empirical base estimates. And one other thing I should mention is what the role of the empirical base estimate is. Essentially, this quantity will allow the empirical Bayesian to mimic the behavior of an actual Bayesian that knows G. So instead, what we want to do in this talk is, instead of focusing on point estimation, to actually conduct inference and move on to confidence intervals. So we essentially want to construct confidence intervals that contain the true or the empirical base quantity of interest with asymptotic frequentist coverage at least 1 minus alpha, similarly to what I explained before. And we want this to hold for all G in this class calligraphic G. And this, throughout this talk, can be arbitrary, but it has to be pre-specified and has to be a convex class of distributions. And I'll come back to this point later. So this is what we're trying to achieve. So just to explain how more I want to give some more examples of data analysis that fall in this framework. So here's a really nice paper by Eric van Zweet, Simon Schwab, and Steven Sen, where they try to propose a way of analyzing RCTs, and especially with a view towards doing shrinkage. So essentially, they think of a randomized controlled trial as being summarized by a z-score, and the z-score follows a normal distribution around a mu, and the mu corresponds to a standardized effect size, and with variance 1. So to interpret this a bit more, imagine there's a clinical trial that's comparing two drugs, and perhaps you run a Cox proportional hazards model. Then Z could be the estimated log hazard ratio divided by its standard error. And by large sample theory, you'd have approximately this Gaussian distribution. And now, to help with inference, it's again convenient to posit this hierarchical model where these standardized effects mu also come from a prior G. But the question again is, how do you actually choose G, or how do you know what G is? And the really clever idea in this paper is to make the following observation. You may not know what G is, but you do have some context about what you're measuring. Namely, it's a z-score from an RCT. So essentially what the authors did is they went ahead and collected another 23,000 z-scores from RCTs in healthcare. And I'm showing the histogram of these z-scores on the bottom left. And then they posited the same hierarchical model for all of these, which then allowed them to actually estimate G. And then with the estimated G, they could proceed as in an actual Bayesian analysis. So one RCT that was of interest to them had a z-score of minus 1.8, which actually in a frequentist framework would not be very helpful because you can see the p-value here would be greater than 0.005. But on the other hand, under a Bayesian framework, you can compute, for example, the posterior mean to get a better point estimate and conduct some shrinkage. Or perhaps more interesting here, you can compute the local false sign rate, which answers the following question. Given that you observed a z-score of minus 1.8, what is the probability that the actual direction is the opposite from what your z-score says? So let's say your z-score says that drug A is better than B, but what's the probability that actually that's not the case? And as I said before, the G that was used in this analysis was the one estimated from the 23,000 z-scores. So for example, it gives a z-score of, the posterior mean of minus 1.12. And the probability that the direction is different, given the z-score of minus 1.8, is about 9.1%. But here one can also ask, what is the uncertainty? What about confidence intervals? Let me give you a third example. So here we go back to the Educational Testing Service in the 70s. And here I'm showing a data set with 13,000 students. Each student took a multiple choice test with 20 questions and 5 choices per question. And on the right, I'm showing the histogram with the frequencies the different student of the scores the different students got. So here most students got a score of 10 out of 20. And the model Lord and his colleagues posited here was that first of all, each student has a latent ability mu that corresponds to their probability of answering any given question correctly. And this also follows an unknown distribution G. And then the actual score each student got on the test is a binomial with 20 trials and probability that depends on the student's latent ability. And here, to better assess its student's ability, one could again compute the posterior mean to get a denoised estimate of the actual ability. And again, G is not known, but they follow an empirical Bayes approach and get this posterior mean function I'm showing on the bottom right. So for each value of Z, so each score a student got, you're basically assessing what is the actual latent ability, or what's your best guess of the actual latent ability. And for example, for a student with a score of 0, you'd still be predicting that they have a latent ability of about 0.25, so better than random chance. But again, the question here is, what about uncertainty? And actually, the problem I'm talking about has not received a lot of attention. So there's some recent work by Efron and Narasim Khan, where they essentially argue that it's important to account for uncertainty in this setting, but they consider parametric models for G. For example, exponential families with a sufficient statistic that's a spline with some degrees of freedom. And in that case, inference can proceed with parametric methods, let's say by using Fisher information calculations and the delta method. When one starts looking at the non-parametric setting, there are much fewer results, and they pertain to specific settings. So there are results on the posterior mean in the Poisson model, and that's the paper I presented in the beginning. There are some results for the posterior mean in the binomial model, and I'll talk more about that later. It's a data set from the last slide. But as far as we are aware, there are no more general results. And instead of this work, we try to present a unified inference framework that works in the general non-parametric situation I described. So to tell you why inference may be difficult in this setting, I want to tell you first about something that's well understood, namely the difficulty of non-parametric empirical Bayes point estimation. And I told you about 4 problems so far that may sound similarly, at least conceptually, but they're actually very different in terms of their statistical difficulty. So first I talked about the posterior mean in the Poisson model. And here it turns out that without assumptions on G, it's possible to estimate the posterior mean at the parametric rate 1 over square root n. So that's a really nice and elegant result. Then I also told you about the posterior mean in the Gaussian model. Here it turns out it's also possible to estimate the posterior mean at the quasi-parametric rate, so on the rate 1 over square root n, up to some logarithmic factors. And this is also a very elegant results that allows application of empirical-based methods, let's say, to the Gaussian setting. On the other hand, I also told you about the local force sine rate in the Gaussian model. So that was the probability of having, of the true effect having a different direction than the z you observed, given the z you observed. And here it turns out that even if you're willing to make smoothness assumption on G, let's say that it lies in a Sobolev class, then the minimax rates for estimating this quantity are polynomial in 1 over log n. So you may collect 100 times more data, but that really won't help you all that much in terms of accuracy. And finally, I told you about the posterior mean in the binomial model, and here it turns out the problem is completely impossible if we impose no restrictions on G, in the sense that the posterior mean is only partially identified. So even with infinite data, we could not know exactly what the posterior mean is. So you may ask, why does the difficulty of estimation vary so much? And that's essentially because we're dealing with inverse problems here. So on the first line, I'm repeating the model we've been looking at, but all we get to observe are the zi's, and these are drawn from the marginal distribution, whose density I'm denoting by f with a subscript g, and that's just integrating the noise density with respect to the prior. So if p is a Gaussian model, then this would just correspond to convolution. And of course, we know that it could be that two marginal densities are close to each other and for some notion of metric, but then it could be that actually the priors inducing them could be very different, right? This is because the convolution is a difficult inverse problem. On the other hand, the question we're asking here is slightly different. We're asking, if two marginal densities are close to each other, then what does this say about the empirical base estimates of interest? And sometimes these may be similar, and sometimes they may not be so close. And this will determine all this heterogeneity of rates. And this then makes our life for inference very difficult for the following reasons. So the first reason relates to the difficulty of distributional theory in these non-parametric mixed models. So for example, studying the non-parametric maximum likelihood estimator and getting distributional results is notoriously difficult. And for example, the result that the bootstrap works for the Poisson problem, it's really based on some very deep results that exist for a class of discrete distributions. But these results seem difficult to extend to the more general problem we're looking at here. But on the other hand, even if we had a distributional result, let's say we knew that our point estimate is asymptotically normal, then the standard approach of forming confidence intervals would be to just report the point estimate plus minus 2 times the standard error. But here we also face a difficulty because this confidence interval is assuming that the bias is negligible compared to the standard error. And this won't be true under partial identification, where the bias actually never converges to 0, or more generally when the problem is of non-parametric minimax difficulty. So then under substantial generality, if one looks at minimax rate optimal estimators and on a problem of non-parametric difficulty, then the worst case bias will have to be of similar order or even dominate the standard error. And since we want to have a unified inference framework across this range of problems, we essentially will propose methods that are bias aware and explicitly account for the worst case bias. And I'll present 2 methods for doing that. So are there any questions so far?
I think we can proceed, Nikos.
Okay, thank you. So let me tell you about the first method we propose. And we call it F-localization, and I think it's a quite intuitive approach. A reviewer called this a common sense approach. The idea is the following. Since we have direct observations Z1 to Zn of the marginal distribution F, let us form a confidence set of distributions that we call an F-localization and denote by calligraphic F of alpha. And I'll give examples of such F-localizations in a bit. But it's just a confidence set of distributions so that the true marginal distribution lies in this set, with asymptotic probability at least 1 minus alpha. So once we have this set of distributions, the F-localization, we can restrict our attention to priors in the class calligraphic G we started off with that are consistent with our data in the sense that the induced marginal distribution lies in this F-localization. And then once we've restricted our attention to a smaller class of priors, we form confidence intervals for the empirical base estimate essentially by projection. So for example, we look at what's the largest possible value the estimate can take among all these priors we're considering. And this gives us the right end of the confidence interval. And we can do the same thing for the left end of the confidence interval. And it essentially follows directly by the definitions here that these confidence intervals will have the right coverage. And also let me note that actually the statement here can be taken uniformly over any type of empirical base estimates one may want to look at. And this is a traditional idea in statistics. So let's make this more concrete by giving you an example of an F localization. So one thing you may want to do is to look at the empirical distribution of the ZIs and look at marginal distributions that are close to it in terms of, let's say, the Kolmogorov-Smirnov distance. And here we take the radius of the Kolmogorov-Smirnov distance based on Massard's constant for the DKW inequality, which is such that the true marginal distribution lies in this F localization with finite sample probability, at least 1 minus alpha. So to make it concrete, let's go back to our binomial example. Before I showed you the frequencies and the histogram of the scores the students got. Now instead I'm showing you the distribution function, and more specifically I'm showing you this Kolmogorov, this band around the Kolmogorov-Smirnov neighborhood of the empirical distribution function, where we expect that with high frequency probability, the true marginal distribution will be contained in. And our inference will basically be based just on this plot. So on the top right, now I'm showing confidence intervals for the posterior mean. So for each value of Z, I'm showing a different confidence interval. And this was constructed based on the Kolmogorov-Smirnov construction on the bottom right. So let me elaborate a bit more. For example, for a student with a score of 0, the lower end of the confidence interval is about 0. So here we're saying the student is perfect at getting every answer wrong. And how did we get this? Essentially, we had to solve a linear program that got us the worst case prior that's shown as this discrete prior on the bottom left. And now on the bottom right in yellow, I'm showing the marginal distribution that would corresponds to the prior on the left. So if that were the prior, then the marginal distribution of the binomial would be this yellow line. And you can see it lies within this Kolmogorov-Smirnov neighborhood. And we can do the same thing for the upper end, where we get a posterior mean of about 0.4, so substantially better than random guessing. And here actually we get, again, we solve a linear program to get the worst case prior. It's this one shown in gray. And again, the induced marginal distribution lies in the Kolmogorov-Smirnov band. So you may ask, why are these point estimates or these ends of the confidence interval so far apart? And one explanation is that the first prior puts the small point mass at 0. And this causes the posterior means to be so different. And the punchline is that at least based on the Kolmogorov-Smirnov neighborhood, we cannot tell if this point mass at 0 is there or not. And this causes the substantial uncertainty we have about the posterior mean for a student that got a score of 0. While for a student with a score of 10, we're substantially more precise. So that was one example of an F localization that's convenient because it works for any type of a likelihood model, and it's universal and has finite sample properties. But depending on what type of noise model you're looking at, you may consider other choices of F localization. So for example, in this binomial setting we're looking at here, you could consider the F localization of distributions with PMFF that are close to the empirical frequencies in terms of this high square distance, and asymptotically with its radius calibrated by high square quantile. And if you actually use this F localization in this problem, you get this confidence interval shown in black. And here you actually get shorter confidence intervals compared to the Kolmogorov-Smirnov construction. What I really like about what I'm showing you here is that actually this high square construction had been proposed by the folks at the Educational Testing Service, so by Lord, Martha Stocking, and Cressy. And their construction, or more specifically their optimization, specifically depends on the binomial model, the posterior mean, and also the high squared localization. And basically what we're doing here is we're generalizing to this broader class of problems by using modern advances in convex optimization. So that's the first approach. I'd say it's quite easy to construct. As I said, a reviewer called this a common sense approach. It has simultaneous coverage over all types of estimates you may want to look at. But you may ask, what about power? And power here will be strong only if the F localization gives a tight characterization of uncertainty. And this won't be true in general, especially because we have simultaneous coverage. So the approach may be conservative. And also the choice of F localization matters in a way that may not be really clear beforehand. So this motivates us to consider a second approach that we call AMARI, for affine minimax Anderson-Rubin inference. And I'll explain all of these terms in turn. So first, let's talk about Anderson-Rubin. So far, I've been telling you how to form confidence intervals for theta. Now, instead, I want to reduce attention to testing the null hypothesis that theta is equal to a constant c. We'll be able to make confidence statements or to form confidence sets for theta by inverting these tests, but I won't talk about this reduction here. So what does this buy us? Recall that the estimand we're interested in is the conditional expectation of a function h of mu given z. And now just by using the base rule, we can write this as this ratio here, where the denominator is just the marginal density at z, and the numerator is this quantity we call a of z with a subscript g. That's just the quantity here. And what I'd like you to note is that both the numerator and the denominator are actually linear in the unknown g. So now if we're testing whether theta is equal to c, just by rearranging the ratio, this null is equivalent to testing whether a minus c times f is equal to 0. And now here's where the absurd comes in. Note that a is linear in G, f is linear in G. So essentially now we're testing whether a linear functional of G is equal to 0. And this brings us closer to traditional non-parametric result that we can use here. So essentially this allows us to just focus on linear functionals. Now the reason we call this Anderson-Rubin is that they consider a very similar approach in the context of the linear instrumental variables model. So by the previous slide, we've reduced attention to linear functionals. And now to do inference for this, we'll actually consider the following class of estimators that are affine in the empirical distribution of the zi's. So more specifically, we'll consider estimators that take the following form. They're a sample average of a function q that may depend on n applied on the observation zi. And the reason we consider this class of estimators is because it's convenient computationally, but it also includes familiar estimators, let's say kernel density estimators, but also minimax rate optimal estimators of linear functionals in the convolution problem. So that's the class of estimators we're looking at, but of course we still need to choose this q. And here, what we'll do is we'll actually try to pick this q also in a data-driven way. So note that each q induces an estimator L hat, and then we'll basically try to pick the q in a way that optimizes a worst-case bias variance trade-off. So before looking at this equation here, let me tell you separately about what the bias term is and what the variance proxy is that we're using here. So for the bias, first of all, here I've just written the definition of the bias. So for this type of estimator, the bias is thus what's shown here on the right-hand side. But we'll take the worst case squared bias over all G in this class calligraphic G of n. And this class calligraphic G of n consists of all priors in our class that are consistent with our data in a way very similarly to the F localization I described before. So we'll ask for the marginal distribution to lie in a pilot F localization, but now at the level alpha that tends to 0 asymptotically. So this will give us a bound on the worst case bias, squared bias of any given estimator in this class. And for the variance, we'll basically use our observation Zi to get the pilot estimator of the marginal density. And then in the expression for the variance, we'll just replace the true marginal density by our estimator of the marginal density. And basically, this gives us a proxy for the variance of our estimator. And now we have this well-defined optimization problem here, where we try to pick the q that minimizes the worst case localized squared bias plus the variance proxy. And actually, there's a lot of technical challenge in solving this problem. It's not a standard min-max problem, but it turns out we can solve it by building upon results of Donoho, Armstrong, Kolesar, and others. I'll be happy to talk more about this later. So in this way, we can actually get this q, and then our estimate of the linear functional is just the average of this function q applied on the observation zi. And we can actually do inference for this quantity as follows. First of all, it's easy to assess the variance of this quantity since it's just a sample variance. From the optimization problem we solved before, we have a bound on the worst case bias. And then we can prove a central limit theorem for L hat, and then we form confidence intervals that are bias aware. So what this means is instead of just accounting for the standard error of our estimator, and let's say multiplying it by 2, we actually also account for the worst case bias and further inflate the intervals to account for that. And essentially for the general class of problems we're looking at and under mild regularity conditions, we prove that this approach has the right frequentist coverage. Perhaps the strongest assumption we make is that the pilot F localization and the pilot marginal density, and remember these were parameters of the optimization problem, we assume that these are constructed by sample splitting. But in practice, we have noticed that the sample splitting, we do not do the sample splitting and we have not observed loss of coverage thereby. So let me show you some results. So first, I'll go back to the RCT example. So that was the randomized controlled trial, where we'll make basically the noise model here is the standard Gaussian. And here we'll actually make the following structural assumption on G. We'll assume that G lies in the scale mixture of centered Gaussians. So Gaussians with a mean of 0 and with standard deviation over which we mix, and we vary the standard deviation from 0.1 to 60. Now, the one reason we consider this class, and I'll give one more reason in the next slide, is that the original authors of this empirical base paper actually estimate the prior G within the estimated G they get actually lies within this class. And note that this class is actually convex. So if we're willing to make this assumption, then on the left, I'm showing two types of confidence intervals. First, for the posterior mean. So the dashed line is the F localization confidence interval. And that was the one that actually had simultaneous coverage. So actually, the whole area here is a simultaneous confidence band for the posterior mean. On the other hand, the blue line is Amari. So that's just the pointwise confidence interval I just explained how to construct. And you can see that here it actually leads to much sharper inference. And we can do the same thing for the local cosine rate. So here, in case we're interested whether the direction of the effect is different compared to the actual z-score we observed. So that's a concrete data analysis example of our method. So now let me illustrate how this method works in the context of a simulation. So in this simulation, we'll take mu's drawn from the prior shown on the top right, and then we'll observe them with standard Gaussian noise again. And we'll take n equals to 5,000. And one thing we want to explore in the simulation as well is what is the impact of the choice calligraphic G in the performance of our method. So here we'll consider two well-specified models. So the first one is a standard model considered in the empirical base literature, which is a location mixture of Gaussians. So here we'll assume the prior itself is also a mixture of Gaussians. And these Gaussians will have standard deviation 0.25. And this 0.25 you can think of as regulating how smooth we're willing to assume that our prior is. So the smaller we take this tau, the more wiggly our priors will be allowed to be. So that's one possible choice of priors. And the second class we'll consider will be the scale mixture of centered Gaussians, just as in the application, where all the components have mean 0, but we mix over the standard deviation. And the reason we consider the second class is that Matthew Stevens has recently advocated for using this class for empirical-based problems, especially in genomics, and he has argued that it enables more accurate inferences provided that it holds. And here we want to see how it plays out in terms of our confidence intervals. So in the first simulation result, we'll specify the class calligraphic G as this location mixture of Gaussians. Now on the bottom left, I'm showing the expected confidence bands of different methods where I'm averaging over the Monte Carlo replicates. So for example, the orange line is an F localization approach. The purple one corresponds to Amari. And on the right, I'm showing coverage. And essentially all methods have 95% coverage except one method, and that's Efron's parametric approach. But perhaps it's not surprising that this does not have coverage because it's using a parametric model that's misspecified. So this is the posterior mean. So let us change the estimand. Let us look at the posterior probability that mu is greater or equal to given z. And here on the right, we see that still all methods except the parametric one have the right coverage. But now if you look at the confidence bands on the left, you see you actually get really wide bands for all methods. And perhaps this is not surprising. As I said in the beginning, estimating this local false sign rate is a difficult inverse problem. So under Sobolev smoothness, for example, you might have minimax rates that are basically logarithmic in n. And what this is saying is that our method still gives intervals with valid coverage, but of course, given the difficulty of the problem, it returns very wide intervals, and it would be impossible to do anything else. But nevertheless, the method automatically figures out how ill-posed this problem is. So now I want to do one more variation on this simulation, where instead of looking at the location mixture, I look at the scale mixture of Gaussians. So now, first I'm showing the expected confidence bands for the posterior mean on the left. I'd say the picture here is quite similar to what we had for the location mixture. But now if we look at the local false sign rate on the right, you see we actually get much more precise inference compared to what we had in the previous slide. So we really see what Matthew Stevens argued for playing out in the data. And what this is really saying is that for some of these empirical-based problems that are very ill-posed, the assumptions we're willing to make on the class of priors also determine how accurate our estimation can ever be, and also how long, let's say, our confidence intervals can ever be. And one nice property of our approach is that it allows specifying this class calligraphic G in a flexible way. So it can be an arbitrary choice as long as it's convex. So one can conduct, for example, a sensitivity analysis, seeing for different classes, how much does the resulting inference vary. And for some estimates, let's say for the posterior mean, inference does not vary all that much depending on the assumptions you're making here. But for other quantities, such as the local false sign rate, it will really depend a lot on the assumptions you're making. So to conclude, even if n is large, there may be substantial uncertainty in the estimation of empirical-based quantities. And here we describe two approaches to conduct inference in this setting. And also our approaches can be used to assess the sensitivity to the choice of prior class. So thank you a lot for your attention, and thank you for inviting me.
Nico, thank you very much for this very interesting talk. I think that you have done great work. And just to pass to the audience, any questions for Nikos?
I mean, I think I'll make a start, perhaps. I mean, it's a fantastic piece of work. I understand the work is empirical based and to some extent non-parametric, and there is a lot of similarity to Bayesian non-parametrics, which is a very different thing, but it has, I guess, a similar flavor in certain aspects. And sometimes in Bayesian non-parametric examples, you know, you try to be flexible, but in fact you implicitly impose lots of structure on your prior. And I guess, I don't know, is that I'm sensing there is a similar sense here. Is that an issue? Is there a, I guess what I'm asking is, you know, can you try to implicitly be flexible, but actually imposing structure without really realizing this?
That's a really good question, and especially I would get this question a lot. Why don't you do Bayesian non-parametrics here? And one answer is that actually, like you said, I think it's hard if you. So let's say in this hierarchical model here, instead of saying G lies in this class calligraphic G, you could put a non-parametric prior on G. And at least for me, it's hard to say what this assumption is really saying. So essentially what we're doing, you can almost think of it as doing a worst case approach, where perhaps this class calligraphic G is the support of the prior you would put on G. And I think to me that sometimes can be more intuitive to specify the support rather than actually specify the full distribution on the priors. So in that sense, I think here it's very clear what we're doing. And also another thing that I didn't talk about is that most of the methods actually tell you what are the worst case priors that lead to the confidence interval you're actually getting. And there you can explore, is my assumption very pessimistic or not? But often it can actually be that you might see that you get some very pathological G's that are the worst case, in which case maybe you may want to make stronger assumptions on your G. But let's say the scale mixture of Gaussians, I think it clearly imposes some assumptions, but I think it's quite explicit what assumptions you're imposing. But yes, I think in this setting, it's impossible to not make any assumptions, or at least for some of the problems we're looking at.
Great, thanks. That's very clear. And also the connection with the FDR is super interesting. So lovely, thanks.
Thank you. Oh, you're muted, I think.
Oh, no, I think you're on mute.
So are there any other questions for Nikos? So I had a similar question with Nikos Amiris. I mean, I guess it would be quite interesting to compare with Bayesian non-parametric schemes like a Dirichlet process prior on mu, or for example. That would be quite an interesting case because I think it's quite natural to assume that mu here are somewhat clustered. Am I right?
I think it depends on the application.
Yeah.
So maybe it's reasonable, maybe for the insurance example I showed in the beginning.
Yeah.
I'm not sure it's for the RCTs, maybe not as much. Maybe there you actually expect more a continuous distribution of standardized effects. But yes, these are just different classes of assumptions. And I think of our assumptions actually as being quite conservative in that we want coverage to hold over this whole class. Mm-hmm. So our intervals can be quite long in some cases, but this relates to the notion of coverage we're interested in.
Nice, great. Are there any other questions for Nikos? I guess we're done. Just a quick one. Is the name Amari related to the famous mathematician from Japan?
It's actually not, and one reviewer pointed this out. So it's just an acronym, but it's...
yeah, I thought it was an acronym, but you know, you could fix that in order to...
Yes, it's not related to the differential geometry and
yeah, exactly.
So
thank you very much, Nikos. It was a very interesting talk, and we would be happy to meet you in person at some point if you visit Greece to get results for that.
Πες το παιδί ότι χρωστάμε να βγούμε έξω και τα λοιπά.
Χαρώ πολύ, σας ευχαριστώ πολύ.
Ευχαριστούμε πολύ.
Ευχαριστούμε και καλή συνέχεια, Νίκο.
Γεια σας.